I often make an analogy with what you see if you have a cup of coffee and you stir this cup of coffee and you drop a blob of cream in. You can see that there's a separate colour of this fluid that takes a while to mix around, and it's stretched and sheared out. So that's you see a lot of this kind of process in the ocean. But the overturning circulation contains those kind of non-linear processes that you associate with chaos, but it also has larger scale patterns. So these things called water masses. So water masses are large volumes of fluid which have particular characteristics. They have a particular saltiness, a particular temperature, and some of them are in contact with the atmosphere within a few years, every few years. And others, the very deep and dense water masses, don't contact the atmosphere for hundreds or even thousands of years in places. And these huge blobs of fluid move past each other because they have different densities. So it's a bit like if you had lots of different plasticine or Play-Doh and different colours, and you get them all and shape them together, mix them together and take a slice through them, you'd see the different colours in this slice, and that's what the water masses look like in the section across the North Atlantic that we take. And what we're trying to understand is, because each of those colours, each of those blobs of plasticine will carry a different amount of heat towards the pole or towards the equator. We're trying to understand what sets the transport of those water masses and what sets the mixing. So if there was strong mixing, you'd see the plasticine, the colour of it would be homogenized. But so in some places we see this, and in other places it's very insulated and the colours stay separate for a long time. So we need to understand those processes, and that's what I'm trying to do with my team, working on inverse modelling.